Hello, this is Jack Jackson. Today we're going to be talking about the concept of a relation. The concept of a relation is definitely one of the top ideas in all of mathematics. It's a very, very, very important idea. We're going to talk about the foundations of this today. And in fact, you can think of an algebra class, pre-calculus, trigonometry, calculus, all of these courses really can be thought of as a study of certain kinds of relations and their properties. So the idea of a relation is very important. The basic outline of what we're going to be going over here is we're going to start by defining what a relation is. We're going to talk about the domain and range of a relation. And then we're going to represent relations in many, many different ways, including set notation, tables, arrow diagrams, verbal descriptions, dynagraphs, Cartesian graphs, formulas, equations, and maybe some other ways as well. Then we're going to talk about some equivalence properties, and then we're going to talk about different types of data, and then a few additional representations of some types of relations. So again, this concept of relation is one of the most important ideas of mathematics, and its basic core is pretty simple. It says we're examining two sets of objects, and there's some relationship between the two sets. So knowing something about the objects in one set tells you something about the objects in the second set. So we start with an object from the first set, and the relation tells us how it is related to objects in the second set. And as I've said, this concept of relation is foundational to a study of algebra and all subsequent courses. And in fact, this course, this algebra course, can be considered a study of the properties and applications of certain types of relations. So we're going to actually define this. And one of the things about mathematics is we have precise definitions of things. And there's actually a couple different ways to go at this, but this is the way we're going to be doing it for this class. I think this is the best definition. So a relation is defined to be a set of ordered pairs. So pretty simple definition, a very general definition, a set of ordered pairs. The elements of the relation are sometimes referred to as points. So the things that are in the relation, as are in any set, are called elements, but we sometimes call them points as well. The domain of a relation is a set of all the first coordinates of the elements of the relation. These first coordinates are also called inputs. The range of the relation is a set of all second coordinates of the elements of the relation, and these second coordinates, I should say, are also called outputs. So the first coordinates are the inputs, the second coordinates are the outputs. And of course we write ordered pairs as parentheses, input, comma, output, parentheses. For example, the ordered pair 3, 4. In this ordered pair, 3 is the first coordinate, that's the input, and the 4 is the second coordinate, that is the output. So notice that this definition of relation is extremely general. It's simply a set of ordered pairs. So any set of ordered pairs of anything is a relation. So often we're going to be considering ordered pairs of numbers, say real numbers or integers or something like that. But the ordered pairs don't have to involve numbers at all. They can be pairs of people, or people in chairs, or temperatures, or stock prices, or it could be anything. So that's why this is such an important idea, is that it's so applicable to so many different ways, that these ordered pairs can be ordered pairs of anything. So certainly one of the big ideas in mathematics is the idea of number, and certainly we will be dealing with number, but that's not all mathematics is. Mathematics really is much more than just dealing with numbers. And this idea of relation is certainly one of the ways that we deal with many, many things, not just numbers. Now we can represent relations in many different ways, and so in the following slides we're going to explore several of these ways. So sometimes one representation is the best way to really see a certain relation, or it may bring out certain characteristics and emphasize those characteristics of that relation. Okay, so we can see some of the structure there. On the other hand, maybe another different way of looking at it also brings out different elements of the structure. And the idea here is if we look at relations in these multiple different ways, then knowing something from each one of these representations should help us understand the other representations as well, and together they give us a really good view of what the relation is. Now it's because of these multiple possible representations and because of how general the nature is of this concept that this is such a fundamental idea in mathematics. And this is also what makes this concept applicable to nearly every area of human endeavor. Pretty much no matter what we're going to be doing, we can find relations involved. We're going to find relationships between things. And so, as you can probably think about just about any area that you might be interested in, there are relationships between things. And so we can describe these sometimes here. Now, National Council of Teachers of Mathematics, NCTM, has this representation pentagram. I first encountered this idea as the rule of three when they talked about doing everything graphically, numerically, and symbolically or algebraically. And then that quickly expanded to the rule of four, which include the verbal, and now this NCTM has expanded it to sort of a rule of five. And so we have this idea that we're going to have five main ways of representing lots of mathematics, including relations. So we're going to have a concrete pictorial way, so we could actually have physical concrete objects. We might explore things that way with some physical items, maybe some manipulatives or some sort of physical thing out in the world. We have graphical ways of looking at it. That's a picture, as well as the concretes they're both pictures, but the graphical gives us ways of writing that, and there's several different kinds of graphs that we can look at. The algebraic or symbolic way of looking at it is when we write down symbols to represent concepts. So we would have some formulas or equations that might represent relations, and we'll have that there. Numerical or tabular way is we actually have actual numbers involved with this. So in the case of where we're having relations that involve numbers, then there's going to be a numerical way of looking at it, and we can have tables of organizing our data, whether it's numbers or not. And then finally, there's a verbal way. So we can explain relations in terms of rules, and we can relate all this stuff in terms of actual sentences and real-world language. And, of course, in our case, we'll be doing that in English, but, of course, whatever language you wanted to speak, you could represent these ideas in that language. And the idea is that all five of these things, then, can be applied to real-world situations. And the other thing is, if you notice with the lines, we have lines going from each of these to each of the others. And so that indicates that these relationships are all connected, that we're representing the ideas in many different ways. So we're going to start going through these slides, and as we go through here, we're going to think of different ways of representing them. As usual, I'm going to stop you from time to time and ask you to come up with some of the answers before you see me review those answers. So please, when I do ask you to pause, do that in the video. So each of these different representations are different ways of thinking of relations. So remember, our definition of a relation is a set of ordered pairs, so certainly we can use a set notation. So here we have a set with some ordered pairs in it, so that by definition that is a relation. So I have three questions for you here. How many elements or points are in this relation? What's the domain of this relation? Now remember, the domain was the set of all the first coordinates. And the range, what is the range? That's the set of all the second coordinates. So press pause for a second here and figure this out and come back when you're done. Press pause now. Well, this relation has five elements. The first element listed is the ordered pair 1, 2. Notice 1 and 2 are not elements themselves. It's the ordered pair 1, 2, which is an element. 3, 4, that ordered pair is a second element. 5, 7 is the third element. 5, 8 is the fourth element. And 8, 5 is the fifth element that are listed. at least in the order that they're listed there. What's the domain of this relation? Well, it's going to be a set of all the first coordinates. So that's going to be 1, 3, 5, and 8. Notice that 5 is listed twice, but when you write a set, you don't, remember, we don't list those things twice. So it's 1, 3, 5, 5, and 8, but the two 5s, you just list one of them. The range of this relation is then the set of second coordinates 2, 4, 7, 8, and 5. In any order that you want to list those. I happen to list them in increasing order here. But in a set, it doesn't really matter what order you list them. But list everything that belongs there exactly once, not more than once, and don't leave it out. So domain is a set of the first coordinates are inputs, and the range is a set of second coordinates are outputs. The input of 1 goes with an output of 2, and so forth. Okay, are these relations, and if not, what's wrong? Why not? And if so, find the domain and the range of the relation. So we have three possibilities here. These are three sets. So are these sets relations or not? If they're not, what's wrong? And if they are, find the domain and range. Go ahead and do this one now. Press pause now. Okay, well now we're back, let's take a look at this and see the answers. Well, this first one is not a relation since it's not a set of ordered pairs. It does have a couple of ordered pairs in it. It has the ordered pair 1, 6 and the ordered pair 3, 9, but the 1 and 2 are single elements and not ordered pairs. So this is not a relation since it's not a set of ordered pairs. The second one, yes, it is a relation with three elements. The ordered pair Bob, Sally is one ordered pair, that's one element. The ordered pair Ted, George is the second element, and the ordered pair Phil, Sarah is the third element, so it has three elements. The domain is a set of first coordinates, which are Bob, Ted, and Phil, and its range is a set of second coordinates, Sally, George, and Sarah. Okay, and the third one is also a relation. Okay, it's got three elements, three ordered pairs. But notice that the first coordinates of these ordered pairs are themselves ordered pairs. So the input for the first ordered pair is the ordered pair 1, 2, and the output is the single number 3. For the second ordered pair, the input or first coordinate is the ordered pair 4, 5, and the output is the single number 9. And of course, the last one, the input or first coordinate is the ordered pair 7, 8, and the output or second coordinate is 15. So this is a set of ordered pairs. So it's a relation that has three elements, three ordered pairs, and its domain is a set of first coordinates. Well, the first coordinates themselves are ordered pairs. So the first coordinates are don't make up the domain, and so that's the set containing the ordered pairs 1, 2, 4, 5, and 7, 8. And its range is a set of all the second coordinates, which are the set containing 3, 9, and 15. So notice that the ordered pairs don't just have to be a single number for the first coordinate and a single number for the second coordinate. You could have more complicated things like an ordered pair for a first coordinate or a second coordinate. You could have people for coordinates instead of numbers. So it's not just single numbers always. Alright, we can also use set builder notation that we discussed in an earlier section. So far we've considered relations just consisting of a few elements, but often our relations will consist of infinitely many points. And we can use set builder notation to give these larger relations. For example, the set of all ordered pairs of the form xy such that y equals the opposite of x and x is an integer. So this has infinitely many points. The domain is the set of integers because it says x can be any integer. And its range then, in this case, turns out to be the set of integers as well, because when we take the opposite of an integer, we get an integer, and eventually they're all used there. So the domain and range are the entire set of integers, both of them. Now, we can list out physically some of the ordered pairs here, but we can't list them all out because there are infinitely many of them. So we need something like the set builder notation or something similar to indicate all of the ordered pairs, but we can write down a physical list. So you can think of this infinite set and kind of see all the ordered pairs sitting in it, even though there are infinitely many of them there. You could never physically write it all down, but nevertheless, there is a set with all these ordered pairs in it. And we can list part of these down, and one way we might do it is with a table. So this would represent the ordered pairs. The inputs are in the top row, and the outputs are in the second row. And of course, one column is one ordered pair. So the ordered pair -4, 4 is one of the points. -3, 3 is another element. -2, 2, and so forth. Now this isn't the entire table. It goes on forever to the right and forever to the left. But it may be a part of it. Of course, this gives us the idea that we can maybe represent relations by a table. So we could take the relation that's the set of these four ordered pairs, 3, 4, 3, 5, 5, 2, and 2, 6. That's a relation, and we can represent it as a horizontal table, like you see here, or a vertical table. Now, if we do a horizontal table, we will assume that the first row is the input and the second row is the output. And if it's a vertical table, we'll assume that the left column is the input and the right column is the output, unless somebody says otherwise. So that's sort of going to be our standard assumption. And again, often our relations are infinitely large. They have infinitely many points, and so in these cases we cannot physically write out the entire table. Nevertheless, the table does exist, even though it goes on forever, and we can write out a representative part of the table that we are interested in examining. So consider a relation of the form x, 2x, where x is a natural number. So we can represent a portion of this table starting at the beginning with the lowest x of 1 for the input. And notice the domain is all natural numbers. So the domain is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so forth, and it goes on forever, all natural numbers. And so we have the first part of the table listed here. And of course the inputs are the natural numbers. The outputs will be 2 times the input. So the outputs are 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, and so forth. And of course we describe that as what? The set of even natural numbers. That would be the range. So again, this table goes on forever, at least to the right. There's nothing in between any of these points that we have here because we're only letting x be a natural number. There's nothing to the left of this because 1 is the lowest natural number. But it does go on forever to the right. So this is only a portion of the table, but it is a representative portion, and we get a pretty good idea of some patterns and structures that you can see there with the numbers. And we can see that by looking at the table. So here's a relation. Consider the relation, the set of all ordered pairs of the form x, x, such that x is a natural number and x is less than 6. Give the entire table in horizontal and in vertical orientations for this relation. Okay, go ahead and get you a piece of paper out and write this table down, at least in both horizontal and vertical orientation, and then come back and check it when you're done. Press pause now. Okay, well you're back. Hopefully you can see that this is the x and the y are the same, the input and the output are the same, and so the input is a natural number less than 6, so the input has to be 1, 2, 3, 4, 5, and the output's exactly the same. And so we can see that there's the table both written horizontally and vertically. Consider the relation, the set of all ordered pairs of the form x, 3x minus 1, where x is a natural number. How many elements are in this relation? Then give a representative portion of the table for this relation. Well, since x can be any natural number, there are what? Infinitely many points in this relation, but we can write down part of them. So why don't you write down, say, the first part of this table with the lowest x's and write out several elements. Press pause and then do that now. Okay, now that you're back here, the first 13 elements of it, even though there are infinitely many of them. This gives the lowest x's from 1 to 13, natural numbers, and we can see the outputs. How do we find the output? We take 3 times the input minus 1. So let's just check some of these and see if I did this right. 3 times 1 is 3, minus 1 is 2, so 1 goes to 2. 3 times 2 is 6, minus 1 is 5, so that's there. 3 times 3 is 9, minus 1 is 8. 3 times 4 is 12, minus 1 is 11, and so forth. And hopefully these are all correct. Okay, here's another table. Rolf, trumpet. Tim, trumpet. David, horn. Scott, trombone. Sam, tuba. Is this a relation? And if so, list the relation in set notation, state its domain and its range. Now, technically speaking, this is not a set of ordered pairs in its notation, but it does represent a set of ordered pairs, so it is in fact a relation. So any of these alternate representations that we have of relations, we should be able to write them out as a set of ordered pairs, since that is the definition of what a relation is. So go ahead and work this out now. Press pause. Yeah, it actually is a relation, and the relation is the set of ordered pairs: Rolf, trumpet, Tim, trumpet, David, horn, Scott, trombone, and Sam, tuba. And its domain is the set Rolf, Tim, David, Scott, and Sam, and that's actually the first names of the Empire Brass Quintet members in 1985. These are some of my teachers that I studied with back then. Its range is trumpet, horn, trombone, and tuba, that set containing trumpet, horn, trombone, and tuba, which is a set of instruments in a brass quintet. Notice that there are 2 trumpets in a brass quintet, but trumpet is only listed once in the range because this is a set. Now, so far, these have sort of just been ordered pairs that have been kind of sitting there in a list or a table or in between a couple curly braces. They're just kind of been sitting there. And we're going to think of it now a little bit more dynamically. So relations we can think of in terms of an arrow diagram, and we can think of a relation as a path or a process that takes you from a first coordinate to a second coordinate. So we're going to start with the first coordinate and follow the path, the relation, the arrow, to get to the second coordinate. Now we're thinking of it more dynamically, so we're going to start somewhere and we're going to end up somewhere. So you got like origination place and destination place. So now it's a little bit more dynamic, some action. So here we have 3, 4, 7. Those are going to be our inputs, our first coordinates. And watch this. They're going to be sent over, boom, to some second coordinates. So 3 gets mapped to 2, gets sent to 2. 4 gets sent to 3. 7 gets sent to 5, and 7 also gets sent to 8. And so we have, this generates some ordered pairs. So this generates the ordered pair 3, 2, and so forth. So there's the same relation. So here's a couple of questions for you, 3 questions. What is this set on the left called? The contents of this kind of pink circle on the left. And then what are the contents of this purple circle on the right? What's that called? And then write this out as a set of ordered pairs. Okay, go ahead and press pause and do that now. Okay, well, the set of inputs is called the domain. So the set on the left is the domain. Okay, and so the domain of this relation is the set containing 3, 4, and 7. The contents of the circle on the right is called the range because it's a set of outputs. The set of outputs is called the range. And the range of this relation then is the set containing 2, 3, 5, and 8. So as ordered pairs, this relation is the set containing the ordered pairs 3, 2, 4, 3, 7, 5, and 7, 8. An old typo right there. That should only have one open parentheses there. I'll fix a couple little typos I've noticed. I'll fix those before I print out the PowerPoint for you, the slides. So we can think of this like, for example, showing a trip. So the domain represents the origination city, and the range represents the destination cities. And so we can have some trips going on here. And so now we're thinking of the trip now. It's not so much as where you start or where you end, but it's the journey that's part of it. And so notice that we're thinking of this a little bit different way, but it's still the same idea. We still have ordered pairs, but we're still thinking of this more dynamic as something is happening now. Okay, so which trips are indicated by the diagram? Well, we've got Fort Smith to Van Buren. That should say Van Buren to Alma, and then Alma to Fort Smith. Okay, what if another way we can think of a relation is by a rule. This would be sort of a verbal way of doing it. And we can put this, the rule that we're going to have in quotes here is something you place between the first and second coordinates to make basically a sentence that makes sense. So, for example, the relation "is the biological mother of" is a relation that we can place between two people. So the first coordinate goes before this, and the second one goes after it. So, for example, Joy Jackson is the biological mother of Jack Jackson because Joy. Well, that's a true statement. Joy Jackson is the biological mother of Jack Jackson. And we have the ordered pair, Joy Jackson, comma, Jack Jackson. And so we can place this relationship between two people, and it basically tells us whether two things are first coordinates, which first coordinate goes with which second coordinate. So give 3 examples of ordered pairs that are part of this relation. And then, are you a first coordinate in this relation? What's the domain of the relation? That should say a second coordinate. Are you a second coordinate in this relation? And what's the range of the relation? Okay, press pause and answer those questions now. Okay, so I already gave this example, Joy Jackson, Jack Jackson. So since Joy Jackson is the biological mother of Jack Jackson, that's my mom and me. Dinah Jackson is the mother of Heather Jackson Hardwick. And Dinah Jackson is the mother of Ashley Jackson. So that's my wife and my 2 daughters there. And so, you could have your own examples that you would put in that. So the first coordinate is the mother of the second coordinate. Are you a first coordinate? Well, it depends on who you are. If you are a biological mother, then you are a first coordinate. Otherwise, you're not. So obviously, this is going to be limited to just some of the female members that are watching this. Okay? But not even all of them. What is the domain of this relation? All human biological mothers. We limited it to humans in this case. But it's all biological mothers. Are you that should say, second coordinate in this relation? And yes, everyone is a second coordinate in this relation because everyone has or had a biological mother. Okay? And so now just what you wanted to be. Now you're a second coordinate. What's the range of this relation? Humans who have or had a biological mother. Well, that's all human beings. So the set of all human beings is the range. Okay, so let's look at another one. Is the square of. So the first coordinate is the square of the second coordinate. What's a reasonable range for this relation? And if you choose that range, whatever you choose, what's the domain that goes with that? And give a representative table from some of the elements of this relation with the range and domain that you chose. And write this relation in set builder notation. Okay, go ahead and see if you can figure that out. Press pause now and come back when you can finish. Well, there's lots of different things we could pick for the range. The range has to be something that can be squared because the first coordinate is the square of the second coordinate. But, for example, we might just restrict this to the set of integers. If you didn't want to do that, you could make it all real numbers. You could even make it complex numbers if you wanted, or rational numbers. There are several different choices you could do. Or you could just pick 3 or 4 different numbers, and that could be the range. Okay, but for me, I'm going to let it be the set of integers. Now, if the range is a set of integers, the domain then is going to be the set of things that are squares of the things that you chose for the range. So if you chose all real numbers for the range, then you get all real numbers for the domain. If you get all rational numbers for the domain, you'll get all rational numbers for the range domain as well. But if we have integers, we're going to get integers here. I take that back. If you take all rational numbers for the range, you're only going to get some of the rational numbers for the domain. And that same thing is going to happen with integers. So if I take the integers for the range, we're only going to get the perfect square integers for the domain. Okay. And in fact, even with real numbers, if you picked real numbers for the range, you're only going to get non-negative real numbers for the domain, because negative numbers are not squares of real numbers. So we'll correct that statement. Okay, so let's do it the way I did it with integers. So if you take integers for the range, then the things that are squares of them will be the domain, which is what are called perfect squares. So, for example, 36 is the square of negative 6, so 36 comma negative 6 is an element of its relation. And here I've made a table of some of the things. So 36 comma negative 6, 25 comma negative 5, 9 comma 3, 16 comma 4, and so forth. So we could write this in set builder notation a couple of different ways. The set of all ordered pairs x comma y, such that y is an element of the integers and x equals y square. Or elements of the form the set of all ordered pairs of the form y squared comma y, such that y is an integer. That's an even more compact way of writing it. Alright, let's look at some more examples of relations given by a rule. So give an example of an element, point or ordered pair, whichever you want to say it, that's generated by each of these relations. Is the biological brother of, is the father of, cubed is the presidential nominee of, has a value of, and there I'm thinking the domain is the U.S. coins. And of course the range would be those particular values that U.S. coins take on. Has hair colored, whatever, is equal to, is less than. So these are relations we can put between different kinds of objects, different kinds of things. So make up some ordered pairs that would satisfy these. And so what happens is these give you ways of testing, okay, to see if things are ordered pairs, okay, and you can test to see if something is or is not there. So for example, 3 cubed is 27, so 3 comma 27 is an ordered pair. But if we try to say 3 cubed is 8, that's false. So 3 comma 8 is not an ordered pair. Okay, so you can test to see if an ordered pair is part of your relation or not by seeing if this rule is satisfied, if it makes the rule true. So go ahead and come up with some ordered pairs for this one here, and then come back when you have your answers. Press pause now. Now it's very important as we go through these different videos that when I ask you to do a problem that you actually work through it yourself. You're going to learn much, much more from these videos if you are an active participant. one of the things that's very important about an online class is we've got to try to replicate some of the active learning that occurs in a classroom. And one of the things that we can do in a classroom sometimes is I can encourage students to be more active and more participating, and we have to be able to do that online. So be sure that you do these problems whenever I ask you. So here's some examples. Jack Jackson, Michael Jackson. Jack Jackson is the brother of Michael Jackson. Is the father of Jack Jackson, Ashley Jackson. Jack Jackson is the father of Ashley Jackson. Cubed is 2, 8. 2 cubed is 8. Is the presidential nominee of Barack Obama, the Democratic Party. Barack Obama is the presidential nominee of the Democratic Party, or at least in say, 2012. Has a value of dime, 10 cents. A dime has a value of 10 cents. Has hair colored. Bruce Wayne has black hair. So there's a fictional character. Okay, Batman has black hair. Is equal to 6 divided by 2, or 6 halves, is equal to 3. So 6 halves, 3 is an ordered pair. Is less than 3, 5. 3 is less than 5. And so these relationships give you ordered pairs. And again, we could check it and see. For example, if we reverse this last one, 5, 3, it would make this statement false. 5 is less than 3. That's a false statement. Okay, so 5, 3 would not be part of this, but 3, 5 is. And of course, each one of these has many, many possibilities. Now, there's some special relationships that some relations have, and certainly not all relations have these properties. These are special properties that only certain kinds of relations have. But we're going to name these properties and see if we can talk about them just a minute. The first one is the reflexive property. A relation is said to be reflexive if and only if A is related to A. Now notice I use this little squiggle to stand for the relation. So the squiggle would be replaced by, say, one of those statements that we had before. So the squiggle might represent is the biological brother of, or is the father of, or whatever. Okay? So we're just going to say is related to, is how we're going to pronounce it here. So a relation squiggle is reflexive if and only if A squiggle A. In other words, A is related to A for every A in the domain. In other words, as an ordered pair, we'd say only way this could happen is if and only if A, A is an element of the relation for every A in the domain. So everything is related to itself. What do you do when you look in the mirror? You see your own reflection back at you. Okay, so you're related to yourself in that way. So an example of a relation that's reflexive is has the same last name as. Okay? So everyone has the same last name as themselves. So that's a reflexive relation. Symmetric relation. Okay? Symmetric property. A relation is symmetric if and only if A related to B implies B is related to A. So in other words, it's ordered pairs. If AB is an element of the relation, then BA also has to be an element of the same relation. So here's an example that's symmetric. Attends the same school as. So if person A attends the same school as person B, then person B has to attend the same school as person A. That's true, so that's a symmetric relation. Transitive. A relation is transitive if and only if A related to B and B related to C implies A is related to C. So in other words, it's ordered pairs. If AB and BC are both elements of the relation, then AC has to be an element of the same relation. So an example of a transitive relation is less than or is greater than. So I'm going to look at is greater than. In place of the squiggle, we'll put the little greater than symbol. A is greater than B, and B is greater than C, says that A has to be greater than C. Think about that a minute. And that makes sense. That's true. So greater than is transitive. Is less than is also transitive. Now if it has all three of these properties, we have a relation that has reflexive, symmetric, and transitive properties. It's called an equivalence relation. And of course the classic equivalence relation is equal to. Notice that A is equal to A for every A. If A is equal to B, then B is equal to A. And if A equals B and B equals C, then A equals C. Okay. So again, these are special properties that some relations have. Some have all three, and they're called equivalence relations. Some relations have one or two of these, but not all three. And of course, many relations don't have any of these properties. Okay, so let me give you a few relations here, and you tell me if it has reflexive, symmetric, or transitive, and if it is, if it's an equivalence relation. So which of these apply to this one, and see if you can explain why or why not. Is in the same book club as. That's your first example. Press pause and do that one now. Well, let's see. If I'm asking if is it reflexive, I'm saying is everyone that's it. Of course, well, what is the domain and range? The domain and range are both people who are actually in book clubs. Okay, so if you're not in a book club, you're not involved in this particular relationship. You're not a first or second coordinate. Okay. It is reflexive because every person is in the same book club as himself. If you're in a book club, then you're in the same book club as yourself. It's also symmetric. If say Amy is in the same book club as Sam, then Sam has to be in the same book club as Amy. But it's not necessarily transitive, or it is not transitive. So let's take an example here. Let's say Amy and Sam are in the science fiction book club. So Amy's related to Sam and Sam is related to Amy. Sam and Fernando are in the mystery book club. So Sam is related to Fernando. Fernando's related to Sam. Sam's related to himself. So we have Amy related to Sam and Sam related to Fernando. But Amy and Fernando are not related because they're not in the same book club. Let's say Fernando's not in the science fiction book club and say Amy's not in the mystery book club. Then Amy and Fernando are not related. Now, as long as this happens even one place, then the relation is not transitive. And so it's not an equivalence relation because it messes up on the transitive part. It is reflexive and symmetric, but not transitive. Okay, here's another one. Let's say represented the same country in the 2012 Olympics. So here we go. Work this one out now. Press pause now. Well, the domain and range are the set of athletes that competed in the 2012 Olympics. It is reflexive because each athlete represented the same country as himself or herself. It is symmetric. For example, if Michael represented the same country as Gabby, then Gabby represented the same country as Michael. It's also transitive. If Michael represented the same country as Gabby and Gabby represented the same country as Serena, then Michael must have represented the same country as Serena. So it actually is equivalence relation since it's reflexive, symmetric, and transitive. Equivalence relations have these three properties, and that also tells us some other things that have to be true about equivalence relations. Not only are they reflexive, symmetric, and transitive, the domain and range must be exactly the same, and the domain and range are partitioned into what we call equivalence classes. Each of these equivalence classes are subsets of the domain, and the union of all the equivalence classes is the whole domain. In fact, that's what we mean by partition in general. So in general, if we have a set and we say it's partitioned, then we have a bunch of subsets, and those subsets don't overlap. Okay, so they have empty intersections, And yet when you union them all together, you get the entire bigger set. So that's called a partition. So that's what we have here. The equivalence classes are subsets of the domain. The union of all the equivalence classes is the domain. All elements within a particular equivalence class are related to each other and to themselves in both directions. A is related to B, B is related to A, and A is related to itself. B is related to itself if they're in the same equivalence class. No element of one equivalence class is related to any element of another equivalence class, so these equivalence classes don't overlap. So in the previous example, each Olympic team, in other words, each country that had a team represents the equivalence class. So we had the American Olympic team, that's one equivalence class. The United Kingdom or British Olympic team, that is also one team, one equivalence class. Alright, now we're going to look at relations given as a process. So now we're going to think of relations, kind of switch gears again, a little bit different way to do it. Think of a process or procedure or machine or algorithm or assembly line or factory, whatever word you want to use this, but what we're thinking is we're taking a first coordinate, we think the input or raw material, and we're going to transform it into the corresponding second coordinate, the output or finished product. Here we're not only focused on what is the input and what is the output, but on the process by which the input gets turned into the output. So again, a more dynamic way, a process. For example, we could take a manufacturing process. Our input is we start with pieces A, B, and C, some screws, and a box. And then the assembly process is the relation. The assembly process goes like this. Snap piece B onto piece A, screw piece C to the assembled pieces A and B, and then finally box up the assembled product. So the input is this set of pieces A, B, C, screws in the box, and the output is the boxed up assembled product. And for each box we have an ordered pair in this process. Okay? And so this assembly process is a relation, right? Where these things are related because they're going to be all these inputs are going to be put together to make up the final product. So we can think of a process of turning an input into an output. So here are several examples here. And so let's see if you can come up with ordered pairs that go with this. Add 3 to the input. That's a process by which the input is turned into an output. Okay, it's a one-step process. The next one has a couple of steps to it. Take the input, add 2, and then multiply that answer by 4 to get the output. Here's another one. Move 2 steps forward. The next one is take a geometric figure and translate it, slide it, 3 units to the right. The next one is paint it blue. So whatever we start with, we're going to paint it blue. Read. We're going to read. The first coordinate is going to read the second coordinate. Reflect a geometric figure about the x-axis. So we're going to start with the geometric figure. We're going to reflect it, and the output's going to be the resulting figure. And the next one is the same thing, but we're going to rotate it instead of reflecting it. Okay? Work out some examples of this. Press pause now. Okay. So we can think of the adding 3 to the input. Just start with any number you want. Let's say 4. Add 3 to that, we get 7. So 4, 7 is the ordered pair. But notice I'm not just thinking of just the ordered pair 4, 7, which is certainly what I've just generated, but I'm also thinking about this as the process by which the 4 is turned into the 7. Okay, the next one, add 2 to the input and multiply this sum by 4. Okay, and so for example I could start with anything I want that would make sense here. So let's say we start with 1. We add 2 to that, we get 3. Multiply that sum by 4, we get 12. So we turned a 1 into a 12 by this process. So that generated the ordered pair 1, 12. 1 was the input, 12 was the output. So if you want to think of this as a factory or a little assembly line or a machine, it turned a 1 into a 12. Move 2 steps forward. Well, if you want to think of this, one of the ways you can think of this is your location. So if you start at a particular location as the input, then you move 2 steps forward, then the output will be your new location. So you can think of this as a relationship between locations. So previous location, wherever it was, 2 steps forward, your new location. So that's very similar to this next one where we translate a geometric figure 3 units to the right. And you see here I have the input, in this case, is sometimes called the pre-image. So you see the blue triangle there is the pre-image. And we take every point and slide it exactly 3 units to the right, and they get this image set here, which is red. So this point right here is the pre-image, and this point here is its image. This vertex here, pre-image point. This one here is its image point. And so we go pre-image to image there, and we can see that. If we are collectively, we can take the entire triangle as a pre-image set of points, and we end up with the image set of points, the red triangle. Paint it blue. We start with the red box. We end up with a blue box. Read. You, your math textbook. You are going to read your math textbook. At least I hope so, because it's got a lot of important information in there that you're going to need to learn for this course. Reflect a geometric figure about the x-axis. So here I took a point. I took the reflections over here. I took a geometric figure. This is a parabola, as it's called, or a graph of a particular equation here. And it's the darker colored black or blue graph here. And then we reflect it about the x-axis. We get the image down here, which is the red version down here. So this point here gets sent straight down to here. This point here gets sent straight down to here. The origin in this one is actually a fixed point. Its pre-image and image point are the same thing. So again, we're thinking about the process by which we take this first figure and turn it into the second figure. So we can take a point and rotate 180 degrees about the origin. Here's a point here, and notice it spins around this circular path, a half circle rotation, and lands here. And so looks like that's the point 2, 3, and it ends up at the point -2, -3. So up to this point, we've been thinking about a relation as any set of ordered pairs of anything, and pretty much every type of representation that we've looked at can be done for pretty much any relation. But now we're going to restrict ourselves to looking at ordered pairs of real numbers. Now, one of the things that's really nice about real numbers, as you know, is real numbers correspond to points on a line, a number line. So every point on the line, every point on the number line, there is a number that goes with that point, a real number, and every real number there's a point on the line. There's a one-to-one correspondence there. That, in fact, is itself a function, right? You can start with the number and then find the point, the physical point on the line, or you can start with the point on the line and then have the number. Those are called inverse relations. One is a relation one way, and then flip the ordered pairs, you get the other relation. Now, what we're going to do here is we're going to take, we're going to look at something called a dinograph. We're going to take an arrow diagram, and then we're going to take the points within that little circle, and they may be all jumbled up, or we're going to write them in order, in fact, place them where they would go on a number line. And then we're going to do the same thing with the points in the range, and we're going to get something called a dinograph. So I'm going to get out of this PowerPoint for a second and show you an example of a dinograph. This is something I put together in Geometry Sketchpad. So the points in blue there are the domain points, and so here we see we have 2, -2, -1, 0, 4, and 1 for the domain, and then they go to certain points in the range. In this case, 4, -2, -4, 0, 8, and 2 makes up the range. And so this is an arrow diagram like we had before. Okay? And what I'm going to do, though, is I'm going to take these points here, and I'm going to line them up in a number line and show where they would go on a number line. So here are the same points here, down here on the number line. Okay? Okay. So let me that didn't do exactly what I wanted it to do. Let me come back to this in a minute. Okay. Alright, here's where we were starting. So what I want to do is take these and put them on the number line. So I'm going to take this point -2 and put it down here on the number line. Okay, still pointing to -4. Point 2 is going to go down here. The point -1, it's got to go here on the number line. The point 0 goes down here at the origin on the number line. Where does 4 go on the number line? Well, it's got to go over here. And 1, it's got to go here. So notice I've just taken these things, and now I've got my arrow diagram, but the stuff on the left really doesn't matter. It's the same points are down here located on the number line, but they're still pointing to here. Now what I'm going to do is do the same thing for the number line here. I'm going to move this 4 to here. The 8's going to go over here. The 0 is going to be here. The 2 is going to be there. The -2 is going to be over here. And the -4 is going to be here. So if you look at it, what do we have down here at the bottom is really the same arrow diagram that we have at the top. Okay? But I have, since these are real numbers inside these sets here, inside the domain and range, then I can place them on number lines, both the ones in the domain, the blue points down here, and the ones in the range, the red points here. Now this is what we call a dinograph. And so it's really just the same thing as an arrow diagram, but it also shows, since these points here, it's these 4, -2, and -4 are not just completely unrelated things. They have an order to them, since they are real numbers. They have a location on the number line. And so what we've done is we've just taken our arrow diagram and done it this way. I've chosen to let the arrows go up. You could do it with the arrows going down, or you could do it with a couple of vertical lines and have the arrows go either to the right or to the left. I chose to do it this way here. And so this gives us what we call a dinograph. Okay? So once again, what I've done is I've just taken the points in the domain, moved them down here to a number line, and taking the corresponding point that was up here in the range and moved it down here to this number line, and now I have these things. Okay? So let's go back to our PowerPoint. And so this shows us that we ended up with what we ended up doing there. So you have a little bit of something for your notes there to show how the dinograph and the arrow diagram relate. This says dinograph of a function. We're going to see in our next unit that our next section that a function is just a special kind of relation. So, and I'm using some function notation here, but we'll get to all that a little bit later. So, this arrow diagram kind of turns sideways with the points placed on the number line is what we have here. In this particular relation, we're considering the relation x comma 2x, where x is a real number, In other words, the y-coordinates, the outputs are twice the inputs. Second coordinates are twice the inputs, the doubling function. And so we can see these set up here, and we have some points down here that we've picked out, and you can see their coordinates. The coordinates here, the values of these points are the first coordinates of these points here, and the outputs are the second coordinates, which are up here. And so you can see these listed as first coordinate and then second coordinate. So for example, the red one here, A, is given by the coordinates 2, 4, and so that's 2 on this axis and 4 on this axis. Sometimes we call a number line an axis. Okay, so we have our input axis, our input number line, and then our output number line. And so that gives us some ordered pairs there. And you can see this actually shows you some structure of what's going on here. It's a way to visually represent what's going on. It's really the same thing as an arrow diagram in a way. So it shows you how inputs and outputs connect, but it keeps those things organized. And we can see some things that are going on in this. So for example, right here, F is very close to 0, and at 0 it would be pointing straight up to 0 here. So that'd be straight up and down. That'd be the only one that's going to stay the same. But notice that these arrows that are when you're to the right of 0, the arrow points to the right, and when you're to the left of 0, it points to the left, and the further you go to the right, the more it goes out. And so that can be an interesting way of looking at it. So let's look back here at this one. Here's the same example here. So here are our input values, and these are actually controlled in this sketch by sliders. So I can actually take this, and notice it is changing the value here, and that one's missing a parentheses, but let's say we take H here, and say put it over here close to -8. There it was. Now it's at -8, and notice Y will be -16 because 2 times -8 is -16. We can also show the dynograph. So as I move this point here, notice here it's straight up and down at 0. As we go here, the arrow points more and more to the right, and we go this way, it's pointing to the left, and more as we go out. Because what we're doing, the distance from here to here is a certain distance, and the distance from here to here is going to be twice that. So from the origin out to the point is going to be a certain distance, okay, and then on the input, and from the origin out to the output point that relates to it, it's going to be twice as far. And we can kind of see that in this sketch. This is given by sliding these points down here. So these are the input points, can be controlled by sliding them around. The red one, you don't slide it. You do it by putting a number in here. So for example, I can say, well, what's going to happen if I put 3 in here? Well, the formula says it's twice as much, so you get 6 for there. We can also change the formula. Instead of 2x, I could say x, let's say divide by 2 instead, and now the arrows are going to point sort of back toward the origin here. And the further out you are, the more slanted they are. So for example, if I put j here at 8 or close to it, let's see if I can get it right at 8, then the related output is going to be half as much, which is 4. So this is a dynamic sketch. One of the nice things about Sketchpad is we can make drawings like this that can kind of come alive. And so the nice thing about this is we can kind of see what's happening and see a little bit of the properties of the function from this as well. Properties of the, well, it is a function. Properties of the relation. Okay, now what I want to do, let me go back to my sketch, is I want to take this, let me go back to just 2x. Okay, and what I'm going to do is I'm going to take this, instead of having both of these axes parallel to each other, I'm going to make them perpendicular to each other. So I'm going to take this and I'm going to turn the axis and line it up so that the origin lines up. So where this is 1, let's see, let's put B at, well, let's look at A. A is at 3 and then 6. Here's its image. So it should be 6 here. Well, I'm going to move that, I'm going to rotate that around so 6 is on an axis going up and down, and I'm going to line the axes up so that the origins, the zeros, are the same here. So this gets a little bit busy. I'm going to hide the dynograph, and now we have basically the same thing as a dynograph, but our axes are perpendicular to each other. So now we can think of input here and output here. Okay, now I'm going to go one more step. I'm going to bend these arrows so that they only go vertically and horizontally. So for example, this arrow from the gray point to the gray image here, from this one here, let's put it at, let's see if I can get it right at 5 or close to it. Yeah, there's at 5 or very close. And then twice that would be at 10 here. So we can go from input to output here, but I can also think of that as going straight up and straight across. And then I can actually put a dot at these corners. So now I can think of this as the ordered pair 5, 10. Okay, and the input is the 5 down here, and the output is the 10 here. Or we can think of the ordered pair as being this point here. That last part we did is called a Cartesian scatter plot. So let me hide the input values, and let's see if I can hide these arrows, and let's hide the axis back in. So now this is what's called a Cartesian graph, named after a famous mathematician, René Descartes, who actually didn't invent this, but he was one of the first ones to really use this type of graphing and really make a connection that this makes between a visual, which is like geometry or visual looking at mathematics, and algebra or numbers. And so this big connection between these two gives us what we call analytic geometry, and that's a very, very important part of studying algebra these days. So we can see, for example, this red point here, 3, 6, is this ordered pair. And notice it lines up with 3 on the x-axis and 6 on the y-axis. So the input axis is the horizontal axis, and the output axis is the vertical axis. And if you notice, I use kind of the generic letters. Often we use X for input and Y for output. There's nothing sacred about that. That's just sort of a generic letter that's often been used. And so this is the Cartesian plot of this particular graph. So this is the graph of this particular relation. So when we normally think of graphing, we normally think of as a Cartesian graph. Now, with these particular points, these particular x values here, there's the domain, or just those x values, and the range is just these y values here, or outputs. And then that generates these ordered pairs. And so these slides sort of get us to that point. So this is where we've rotated it. And it's still pretty much like a dynograph here, where we have a 1 point for the input, 1 point for the output. And then by moving this to the corners here, going straight up and across, these points here in the corners along here represent both the input and the output. So I can get rid of the other part and the input and output is represented only by these particular points. So one point represents the whole complete ordered pair, not just the input, not just the output, but both together. So for example, the green point here represents the point 4, 8. 4 is the input, you go up to that point, go across, and the output is 8. Now, at this point, we were just saying these were just these particular x values was the domain, and these particular y values is the range. You can see the x and y values are first and second coordinates over here in these ordered pairs. But we might say this is only part of our relation. We might extend this to all real numbers, and that's basically we just play connect the dots. I'll be a little careful about that because in not every case should the dots be connected, but in this case they should. And if we look at the graph of all possibilities where the output is 2 times the input, where we let the domain be all real numbers, the range in this case turns out to be all real numbers as well, and we get, in this case, a nice solid purple line. Okay, so here's a, unfortunately the questions, the answer's already up here. What is the domain and range of this particular dynograph? So you're supposed to have just started with this dynograph down here and see if we can figure out the domain and range. So if we look, the domain is down here. It's the set -6, -4, -2, 0, 1, 2, 4, and 7. This is what I have there. The range would be the set of points here. You can read off of this one here. -3, -1, 1, 3, 4, 5, 7, and 10. So the table of elements are -6, -3 here, -4, -1, -2, 1, 0, 3. What do we have here? 1, 4, 2, 5, 4, 7, and 7, 10. Now, if we examine this a little bit, we might notice some structure in the formula and the table. We might notice some structure in the graph. Like, well, let's just look at that. What structure do you notice in the graph? Looks like to me we're graphing parallel lines on these arrows here. Okay, and it looks like each point moved how far to the right? Each point's going to the right as we move up there. And how far? It looks like 3. So it looks like maybe the formula would be what? The output is the input plus 3. Does that work? -6 plus 3 is -3. -4 plus 3 is -1. Yeah, I believe that works. And you can check that out and see that it does. So there's dynograph of y equals x plus 3. Now this one is a Cartesian graph, and suppose these are the only points, no connecting the dots here, just these points. So it has 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. Don't count this one here at the origin. So there are 9 elements there. So if it only includes those, what's its domain, what's its range, and then make a table of the actual 9 elements. So go ahead and do that now. Press pause and come back. Okay, well the domain we need to list all the first coordinates, which are -4, -3, -2, 0, 1, 2, 3, 4, and 5. And the range we need to list their output coordinates. Start down here. -2, -1.5, 0, looks like 2.5, 6, and 10.5. Looks like. And so we do that by lining up, right? So the domain are the points here on the horizontal axis, and the range is here. So one way we could think of the domain is like shine a light, and these arrows are kind of backwards from the ways I've got them here, and it shines a light, and this green one casts the green shadow at this point H down here. And then just read it off of that number line what its coordinate is, and that's part of the domain. Or it's the x coordinate or first coordinate at this point. And the same way for all these. So we shine a light up, maybe you have to do it up or down, and it's projected a shadow on the x-axis, and then we can find the domain there. Likewise, project our shadow on the y-axis or vertical axis, and that gives us our output values, our second coordinates, and then that also gives us where the range is. Okay, and so we can see that. Notice in the range we had some duplications here, and we only list those once. So 6 occurs here and here, both on this point, -4, 6, that's this one, light blue, and 4, 6, which is this tan one here. And so, but 6 is only listed once in the range. And again, you can list these in any order you want. I happen to list these in increasing order for the domain, but I didn't in the range. Okay. Alright, here's another one. Now this one's a connected thing. Notice it has an open dot here, means it's going up to but not including this point right here. And let's assume these endpoints are integer values, coordinates. And then, well, the endpoint is included here. And these points in between are included along this curve. So what's the domain and range of this particular relation? See if you can figure that out now. Press pause now. Well, we can do this the same way as the last one, except instead of individual points, we've got a whole bunch of them. So again, we can shine a light on this and cast a shadow on the x-axis. It's going to start here at -4. This is going to include points between bigger than -4, and then we got to shine a light from below here, and it's going to go up to +4. We can see that as the red line segment there. Okay, and we can read that red line segment as an interval on the x-axis, the input axis, and we can figure it out from there just by reading it off of there. So it's the interval from -4 to 3 is the domain. Does not include -4, it does include 3. So it's parentheses -4, comma, 3, bracket. The range we can similarly do by projecting on the y-axis or vertical axis. So this point down here, we're going to assume this is right at -10. It comes straight across, puts a dot there. These guys here continue to go up here. Some of the points in here double up. Now this one doesn't add anything to the domain, to the range here, because it's an open dot here, but there is a closed dot here that fills in that spot. And up here we have some of the things twice. Doesn't matter. If it's there once, it's already, once it gets in the range, it's there. Once it's in a set, it's in a set. And the top point is the very top of this curve, and that happens to occur right here at 8. Okay, so we go from -10 to 8. Remember, when we're doing intervals, we go left to right or bottom to top, lesser number to greater number. So this is the closed interval from -10 to 8. Bracket, -10, comma, 8, bracket. Alright, well, we've already seen relations in many different ways. Let's look at some more. An equation or formula with two variables generates a relation. We just have to know which variable stands for the input or first coordinate and which variable stands for the output or second coordinate. So a variable in this case is just a placeholder for input or output. And so the equation is basically like giving us the rule to test if an ordered pair is part of the relation or not. So the plain vanilla generic letters used for relations are x for input, first coordinate, and y for output or second coordinate. So that gives you ordered pairs of the form, x comma y. Now if you see x's and y's, we're going to assume x is input and y is output unless somebody tells you otherwise. Now, we'd really rather not use x and y because x and y are just sort of generic, do nothing kind of letters. Okay, we prefer to use more suggestive letters. For example, if we're dealing with time and velocity, where time was the input, velocity was the output, we'd have ordered pairs of the form t comma v. And we'd use the letters t and v because t tells us, they were, kind of suggest that, oh yeah, this is time, and v is, oh yeah, that's velocity. And so we'd much rather use suggestive letters rather than the generic x and y. Okay? But we're going to assume if we have x and y that x is input, y is output. If we have other letters, we may need to be told or figure out somehow which one's input and which one's output. Now, if we just have an equation and we don't have any other things down there, we're going to assume for this course that we're staying inside the real numbers and not going outside of that, say to the complex numbers or something else. So we're going to be looking at just real numbers, and we're going to assume that unless somebody says something otherwise, that we have the largest possible set of real numbers for the inputs and the largest possible set of outputs for the that are also real numbers, so that we get the largest possible sets of real numbers for the input and output. Sometimes, well, you say, well, why wouldn't that just be the real numbers always? All the real numbers, why don't you just make it easy and say that? Well, sometimes there's something in the formula that would prohibit us from allowing all real numbers to be involved. For example, if it involves division, remember we cannot divide by 0, for example. Or if it involves an even root, we cannot take an even root of a negative and still end up being a real number. So, for example, when I write y equals 3x, that means I'm looking at the set of ordered pairs of the form x comma y such that x and y are real numbers, and we have this relationship between the y and the x so that y equals 3 times x. In this case, there's nothing inherent in the formula that would prohibit using all the real numbers for x's and all the real numbers for y, so the domain and the range are both the entire set of real numbers. Now again, this gives you a little rule to check and see. If we take 3 comma 9 is an element, because if we plug 3 in place of x, we've got on the right side 3 times 3, which is 9. We plug 9 in place of y, so we got 9 equals 3 times 3. That's a true statement, so 3, 9 is an element. But if we try to say 4, 5, we put the 4 in place of the x, the 5 in place of the y. We said 5 equals 3 times 4. Well, that's a false statement, so 3, 4 is not part of the relation. It's not an element in the relation. So here we're just going to test to see if these points are elements of the relation or not. So I've got 6 test points, and I've got 5 different relations to test them with. So test these and see if these are part of the relation. So in the blanks, you're going to either put yes or no. So in this first blank in the upper left corner, we're going to put yes if 0, 0 is part of the relation y equals x. If it makes that equation true, then it will be an element of that relation. It will be in the table for that relation. It will be on the graph for that relation. If it's not true, if it makes it false, then put no in that blank. Go ahead and fill out this entire table. Press pause now. Alright, let's check this and see if I've filled out this table right. So I'll go across like we read. 0 equals 0, that's true, so yes there. 1 equals 0, 0 equals 1, that's false, so I'll put no here in this next one. 0, 1. 1 equals 0, false, so this is no. 1, 1. 1 equals 1, true, so this is yes. 1 equals negative 1. No, that's false, so no. Negative 1 equals negative 1. True, so yes. So 0, 0, 1, 1, and negative 1, negative 1 make this equation y equals x true, so they're in the table, in the graph for that equation. They are part of that relation, elements of that relation. Whereas 1, 0, 0, 1, and negative 1, 1 are not in the table for that relation. They do not make that equation true. They are not part of that relation. They are not on the graph of that relation. Y equals x squared. 0, 0. 0 squared equals 0. That's true. So yes, that's part of the relation. 1, 0. 1 square equals 0. That's false. So no. 0, 1. 0 square equals 1. That's also false. No. 1, 1. 1 square equals 1. True. Yes. Negative 1 square equals 1. Yes, that's true. Negative 1 square equals negative 1. That's false. So no. Try the next one. 0, 0. The opposite of 0 is 0. Yes, that's true. The opposite of 0 is 1. False. So that one's not. The opposite of 1 is 0. False. No. Opposite of 1 is 1. False. No. The opposite of 1 is negative 1. Yes, that's true. The opposite of negative 1 is negative 1. No, that's false. So 0, 0 and negative 1, 1 are the only ones that satisfy, of this group, that satisfy that equation. They will be in the table for that, whereas the other ones will not. Y is the absolute value of x. Absolute value of 0 is 0. True. Absolute value of 0 is 1. False. Absolute value of 1 is 0. False. Absolute value of 1 is 1. True. Yes. Absolute value of negative 1 is 1. True. Yes. Absolute value of negative 1 is negative 1. False. So no. Y equals x plus 1. 0 plus 1 equals 0. False. 1 plus 1 equals 0. False. 0 plus 1 equals 1. True. So that's yes. 1 plus 1 equals 1. False. Negative 1 plus 1 equals 1. False. Negative 1 plus 1 equals negative 1. False. So of these, the only one that's actually makes this one work is 0, 1. So again, the rule, the equation is basically the same as giving us a rule, and it tells us whether or not an ordered pair is part of the relation or not. So we can just use the equation to test. We can also use the equation to find out which are the possible second coordinates if I know a first, or first coordinates if I know a second. So here are some relationships. The first one is y equals x squared, the next one is x equals y squared, and the next is y equals x plus 2. And I've given you some of the ordered pairs. I've given you half of an ordered pair, and I'm asking you to tell me what the other half of the ordered pair is going to be. In some cases there might be more than one possible answer. Okay, see if you can work this out. Okay, so for other words, in this first one, let's just make sure we know what we're doing here. In the first one here, I'm telling you x is negative 3. I'm telling you y equals x squared. What is y? And of course, it's negative 3 squared is positive 9. So 9 is going to go in that box right there. Fill out the rest of this. Press pause now. Okay, I have this. Whoops, for some reason I don't have the first one finished there. So let's go ahead and do this one out loud here. Negative 3 squared is 9, so this should be 9. This is 4, 0, 1, 4, 9, 16, and 25. Okay? This one, I have 36 here. It could be either 6 or negative 6 could go here. In fact, we would actually have two entries in the table, really. One is 36, negative 6, and another is 36, 6. Same way here. I'd have 4, 2, and also 4, negative 2. 1, negative 1. Okay, 0, 0, 1, 1, and so forth. And so we get those possibilities there. And this is x plus 2, negative 2 plus 2 is 0, negative 1 plus 2 is 1, and so forth. So you can see those there. I'll go back and fill this out before I print out the, so you have it for your printout. Alright, a few more slides here. We're going to talk about types of data. So when we have things that we're measuring in the real world here, we have two main types of data, qualitative and quantitative. We can kind of classify them that way. Qualitative data is non-numerical. It's basically just attributes and categories only. Quantitative has some sort of numerical scale. If you have quantitative data, we have basically two types that we can split that into. One is discrete and one is continuous. So discrete data is finite or countably infinite. We can list out the values like counts. So there are either just so many possibilities and it stops. So you could, if you wanted to, you could count the possibilities. 1, 2, 3, 4, 5. That's it. Boom. Or maybe it goes on forever, but you could still sort of count them. There's the first one, the second one, third, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, even though it goes on forever, but they're discrete. Whereas if you have continuous, they're uncountably infinite. So, for example, that might be over an interval of real numbers, like all the numbers between 0 and 1. There are not only infinitely many there, that's actually it's actually uncountable. You can't go through there and put them, say, okay, there's 1, 2, 3, 4, and count them that way, even up to infinity. So, for example, quantitative data that's discrete would be maybe you're just counting how many defective items you have in a sample that you've taken off of a manufacturing process. Continuous is we're measuring things like heights or weights. So, for example, if I'm measuring the height of something, I may round it off to, say, the nearest inch or the nearest centimeter, but if I had a fine enough measuring device, I could measure it finer and finer and finer, more finely, all the time, so that I can get a more and more precise measurement. So, in fact, every possible value on a number line could maybe be a height. Well, say from 0 up to some, at least up to some maximum height. There are 4 levels of data. We have nominal, ordinal, interval, and ratio, and that has an order to it. Okay, nominal data is the lowest, then ordinal, then interval, then ratio. So nominal data is categorical. When you have only the names of categories, and there's no inherent order in nominal data. So mathematical operations don't make sense. We don't even have order operations, don't even have order relations between there. And we can't take these and add, subtract, multiply, or divide. Even though they might actually have numbers assigned to them, you may have category ABC or category 1, 2, 3, but if they're really just categories, then those numbers are just labels. They're not really numbers in terms of having something you can do with them in terms of adding and subtracting and so forth. So examples of nominal things that you can measure that are nominal measurements, things like color, the manufacturer, the brand, the flavor, which political party somebody's in. Things like that are nominal. There's not an inherent order to them. They're just categories. Now, if you have categories, but then you also have an inherent order to the categories, that's ordinal data. That's going to be a discrete level there. And subtractions and divisions really still don't make sense. But there is some order to it. So things like a Likert scale. A Likert scale is these scales that go something like, strongly disagree, neutral, agree, strongly agree, or something like that. Those are Likert scales. They have an order, but they're not really, you can't really do too much with them in terms of other things. Sizes, small, medium, large. Those are ordinal type of things. There's definitely an order there and within the categories. Interval data has both order and a scale to it. So addition and subtraction make sense, but there's only one slight difference between interval and ratio data, and the interval data has no natural zero. Because of that, multiplication and division don't make sense. And really, interval data is pretty much limited to dates and temperatures. There's no really inherent zero date. Our calendar is based on a particular date that's sort of starts it out, but it doesn't really make sense in that sense. And temperatures is kind of the same way. So, for example, a temperature of 10 degrees, let's say Fahrenheit, and a temperature of 20 degrees Fahrenheit doesn't mean that it's twice as that the 20 is twice as warm as the 10, because the 0 doesn't really mean the absence of all heat. Okay, it might be on the Kelvin scale, but not on the Celsius or the Fahrenheit scales. So you can't really divide, but you can subtract. You can say from 10 to 20, is a difference of 10 degrees, and that's exactly the same difference as between, say, 90 and 100 degrees. It's still a 10-degree difference. So differences do make sense. The highest level is ratio data. You have order scale and a natural zero. Could be discrete or continuous. And so now all of our algebraic operations or arithmetic operations, add, subtract, multiply, and divide, all make sense. So an example of a discrete one would be counting things, weights, heights, things like this are ratio data, and there we have the most information. So the order is nominal, ordinal, interval, ratio. Notice it spells a word, noir. So let's see if you've followed that, and tell me what kind of level of those four levels of data, nominal, ordinal, interval, and ratio, which of those four applies in these particular cases. So go ahead and press pause and figure this out now. Well, let's take a look. Mass of a coin is a ratio. It has order and scale and natural zero. We can add, subtract, multiply, and divide and make sense of that. Zero mass would mean there's really nothing there. So it has a natural zero. It has order to it. It does work. So that's ratio, highest level. The year of a flood is interval. It has order and scale where the differences make sense, but ratios do not make sense since there's no natural zero. The color of an automobile is nominal. It's categories only. There's no order to it inherent. Ratings on a survey, like strongly disagree, disagree, agree, strongly agree, that's ordinal. They have an order to them only. Flavor of M&Ms, that's nominal. The categories only, no order. You have your peanut M&Ms, your milk chocolate M&Ms, your almond M&Ms, etc. The number of M&Ms in a bag is ratio. It has order and scale, natural zero. You can add, subtract, divide, multiply. They all make sense. Political party that somebody belongs to is nominal. That's categories only with no order. The diameter of a piston is ratio. It's got everything. Order, scale, natural zero. And all your operations make sense. Now, tell me if these are qualitative or quantitative. And if it's quantitative, classify it as discrete or continuous. Press pause and do these now. Okay, the mass of a coin is quantitative, and that's a continuous thing. The mass can take on any value on a real number line from 0 up to some reasonable upper limit. The year of a flood is quantitative, but it's discrete because it's just, you have chunks. It's a certain year, and that's the next year, and the next year, and you don't have half years because we're already saying which year is it. The color of an automobile is qualitative. The ratings on a survey are qualitative. The flavor of M&Ms is qualitative. The number of M&Ms in the bag is quantitative, but it's discrete. They're just counts. Political party is qualitative. The diameter of a piston is quantitative, and it is continuous. Now, the kinds of graphs that you use may depend a little bit on what type of data we have. So if we have qualitative data, for inputs, and we might have counts or percentages for outputs, that can be represented by certain types of graphs. So if we're really interested in deciding if something is a part of a whole, we can take some shape and divide that whole up into areas that are proportional to the percentages that it makes of the whole. For example, in a circle, we have a circle graph, or sometimes called a pie chart. Here we're thinking of the input as being the political party of the U.S. presidents as of the date of this particular recording. We've had 14 Democratic presidents, 4 Democratic Republican presidents, 2 Federalists, 4 Whigs, 1 Unionist, and 18 Republicans. Okay, so the output could be the counts. That's one relation. Or another relation, the input is the party and the output is the percentages. So the percentage, 32.6 of all presidents were Democrats, that would be the output would be the percentage. And if your outputs are percentages, then a pie chart is one way that they're done. Actually, anytime you can do a pie chart, it's probably better actually to use a bar graph. And we could have bar graphs here, and the height of the bar represents the output. In this case, the height of the bar is the count. The height of you could change the vertical scale over here, and the graph would look the same, but the scale would be different, and it could be the percentages that we saw on the other graph as well. And you get it really everything that you got on the other graph for the circle graph, you get here. This one's a little bit easier to read. One thing that you definitely want to be sure that you do when you have a bar graph, though, is if you're going to draw the bars, they must start at 0. And so the height of the bar, as well as the area of the bar, as well as the top of the bar, all really help indicate the output value. Notice this is categorical data. Our input are just nominal data for this, and I have these put here. I guess it looks like they've got them in alphabetical order, but there's no inherent really order to that. That's kind of a forced order. Okay, and so the bars are non-touching bars. There's nothing between these. They're just discrete categories. Okay, a couple other multivariable examples. Sometimes the input is an n-tuple of numbers and the output is a single number. For example of something like this, the arithmetic mean or average of an n-tuple of numbers is found by adding up each coordinate of the n-tuple and then dividing by the number of coordinates. So the input could be the ordered pentuple 3, 4, 4, 5, 6, and the output is the average of those numbers 3, 4, 4, 5, and 6, which is 3 plus 4 plus 4 plus 5 plus 6, and then divide by 5 to get 4.4. So if you think of this as an ordered pair, the first coordinate is the ordered n-tuple 3, 4, 4, 5, 6, and the output is or second coordinate is the output, the average of the input, which is 4.4. So again, we can still think of this as an ordered pair, but it's a little more it's a little more complicated. Well, not necessarily more complicated, just different than just a simple number for the first and a simple number for the second. But again, we still start with an input and we got an output. Okay? We could have the z equals x squared plus y squared. Now in this case, the ordered pair xy is the input and the output is the z. So the z is the output. The ordered pair xy is the input. So if we start with an input of the ordered pair 2, 3, that is x is 2 and y is 3, then the output is 13. Let's see if that works out right. 2 squared is 4, 3 squared is 9, 4 plus 9 is 13. So the output is 13. Now a lot of times we'll write that not as ordered pair 2, 3, comma 13, but as the ordered triple 2, 3. I should say 13, not 14. Should write that as 2, 3, 13. And but it still could be thought of as an input of an ordered pair and an output of a single number. So we can still think of that as a relation. Okay, so oh, there we go. I was going to say there should be one more slide. There it is. So we should have some goals and objectives that we can do. So what should we be able to do after this? We should be able to define a relation. We should be able to represent relation in a variety of ways, including things like arrow diagrams, dynagraphs, Cartesian graphs, rules, verbal rules, processes, tables, formulas, graphs, equations, lots of different ways. We should be able to define the domain and relation. We should be able to determine the domain and range of a relation in any of the forms that we discussed. We should be able to identify input-output order pairs in each of the representations that we've talked about. We should be able to define the properties and determine if a relation has these properties, specifically reflexive, symmetric, transitive, and equivalence relation. We should understand the levels and types of data and classify measurements according to the level and type of data. And of course, ultimately, we'll be able to choose an appropriate visualization based on the type of the data that we have. Okay, so there's a basic introduction to relations, and in fact the entire rest of the course will be looking at specific types of relations and looking at the structure that we see in each of these different forms, the structure of the table, the structure of the formula, the structure of the graphs, different kinds of graphs. And so by looking at these different structures, we'll find them in patterns. Structures will transfer from one form to another, and we'll see how these all connect, and of course ultimately how we'll connect all these to real world situations. So this idea of a relation is one of the really, really big foundational ideas in mathematics, and we'll be building on this the rest of the semester.